Welcome back. In the previous lecture, we were discussing on the thyristors and we discussed some of the commutation techniques of thyristors. This lecture, we will focus on the triggering circuits of the thyristors. So let us see the summary of the discussion, what we are going to do. First, we will introduce what is thyristor triggering, what is gate triggering method, and the types of the triggering circuits. We will focus on the resistance triggering circuit, the RC triggering, and a special type of triggering which is known as the UJT triggering, and some of the advanced triggering circuits as well. We will compare and select the method which is suitable for a particular application of the triggering. The protection and the practical considerations also we will discuss, and what are the modern developments, and then we will conclude with this lecture. So to begin with the thyristor triggering, we have seen in the previous lectures that thyristor will not turn on its own and it is a control device. So we need to trigger it with the help of gate signal. So the turning on of the thyristor is known as the triggering. There are different triggering methods available, such as the forward voltage triggering, which is exceeding the forward breakover voltage, which is denoted by VDO. There is other triggering which is dB by dt triggering. This we have also discussed in the previous lecture, that it is a rapid voltage rise across the anode to cathode. The temperature also plays an important role in triggering, and hence we have to maintain the temperature up to a limit. So excessive junction temperature may cause the triggering of the thyristor, which is undesirable. There is light triggering, which is photon bombardment method, where the light activated thyristors are special type which were used for this triggering. The gate triggering is the control current injection through the gate termini. So this is what we are going to focus, which is generally used for the triggering method. So the classification of the triggering method may be, the triggering may be abnormal, which is undesirable, such as the forward voltage triggering, dB by dt triggering, or temperature triggering. There may be control triggering, which is with the help of gate triggering, and this is the most common and reliable. Some of the special application of the triggering is the light triggering, which is generally used in high voltage series connection. So we are going to focus on the gate triggering method, which is the most common and reliable, and this is controlled triggering. So the basic operating principle of the gate triggering method for a thyristor is that it must be forward biased. Unless and until the thyristor is forward biased, even you apply the gate signal, the thyristor will not turn on. So what is the meaning of forward biased? We have seen that the anode will be positive with respect to cathode, and a certain amount of voltage will be given above the threshold limit, then only the thyristor will be in the forward biased. So the gate signal which is now applied will provide a triggering current, and the gate triggering has to be more than the threshold limit. The gate voltage also need to be exceed with the threshold limit, so we can say the gate voltage should be greater than equal to the gate threshold limit. Now we can calculate the power dissipation also as the product of the gate voltage and the gate current. Now what type of signal can we give in the gate? It can be DC signal, which is continuous gate current, or you can give pulse, which is short duration high amplitude signal, AC signal, which are basically the rectified sinusoidal waveform converting the AC to DC. High frequency pulses also can be used, which is for precise timing control. So these are the type of the gate signals that we can give. We need to control the firing angle, which is alpha, and the firing angle is controlled such that omega t is equal to alpha when the gate voltage is greater than equal to its threshold limit. The gate characteristic and some of the requirement are some of the critical gate parameters, which is VGT, which is the minimum gate trigger voltage, should be between 0.7 volt to 3 volt. IGT is the minimum gate trigger current. It should be in the range of 1 milliampere to 50 milliampere. The maximum gate cathode voltage given by VGT is typically around 10 volt. IGM is the maximum gate current, which should not exceed on an average such as 1 ampere to 2 ampere. PGM is the maximum gate power dissipation. So we need to control the gate current such that it doesn't exceed the gate power dissipation limit. So in order to have a proper design of the gate circuit, we need to obey the conditions such as the gate current should be greater than its minimum gate trigger voltage to have it to be on, and the voltage also should be greater than the minimum limit to turn on. There should be a maximum limit for the current and the power, which is the current and power of the gate should be less than its maximum limit. So what is the ideal gate current waveform? So if you see the characteristic of the ideal gate signal, it should have a fast rise time because a quick turn on can be possible with minimum switching losses. Sufficient amplitude should be there where the gate current should be greater than the basic triggering limit for reliable triggering. It should have adequate duration until the anode current exceeds the latching current, and it should have low power also so that it has minimum gate drive power consumption. Gate drive circuit requirement generate appropriate gate voltage or current, because if this gate voltage and current is not met, then triggering cannot take place. It should have proper electrical isolation, which is often required, control the firing angle precisely, and protect against reverse gate voltage. So if you see the ideal gate current waveform, it will have a sufficient duration, which is for the triggering. Alpha is the controlling factor, and here we have on the x-axis the time axis and the gate current on the y-axis. So this is one pulse which is shown of the gate current, and its total duration is 100 microsecond typically, and 5 microsecond is the duration of the pulse. So this is the ideal gate current waveform, how it looks like. When we classify this triggering circuit, it can be classified into some of the common triggering circuit types such as the resistance triggering, resistance capacitance combination triggering circuit, RC full wave triggering circuit. There is something which is known as UJT, which we will discuss in the form of relaxation oscillator triggering circuit. There is transformer coupled triggering circuit and optically isolated triggering circuit. So these are the common triggering circuit types which we use to turn on the thyristor, and these all are gate triggering methods. What are the selection criteria that need to be followed is firing angle range is required. Isolation is very important. We should focus on the cost and the complexity which is involved with these methods, whether the method is reliable and temperature stability is there, and the power handling capability. So these selection criteria has to be obeyed to select a proper triggering method. Now here we have the gate signal waveform. So we can see the various gate signal waveform for different triggering method. Now here you can see the signal is sinusoidal in nature, this is square in nature, this is pulse, and this is rapid pulse. So there are different types of gate signal waveforms which can be used for the gate to trigger on. Now we will see the first one, which is the resistance triggering circuit. So the circuit description for the resistance triggering circuit involves two resistors R1 and R2, and this is the simplest triggering circuit method available, and we require one diode. So R1 is the variable resistance for firing angle control, and R2 will stabilize the gate resistance. There is a diode which is to have the unidirectional current flow protection. The current path will be from the source to the resistor R1, then the resistor R2, then it will go to the diode, and then the gate cathode circuit will be completed. So the operating principle of this resistance triggering circuit is that the gate voltage will be derived from a supply which is AC, and it will be having a resistance voltage divider circuit. So the gate voltage can be calculated from the parallel division rule is the source voltage multiplied with the parallel combination of the resistor R1 and R2. Firing occurs when we have the gate voltage which is greater than the minimum limit of the gate threshold. The design constraint and analysis is that if we want to prevent the gate damage, then the maximum value by the resistance minimum should be less than the maximum amount of the current. So Vm is basically the peak supply voltage, and we here the R minimum is given by the summation of the two resistors R1 plus R2, where the R minimum should be greater than equal to Vm by Igm. So this equation will come from here. So this is the gate current limitation. Gate voltage protection we required. So maximum voltage which can be applied to the gate cathode must not exceed the VGM value. So here this relationship will give you the value of the voltage which you can apply at the gate, and this should not exceed the maximum limit of the gate voltage. The minimum gate current that is required for reliable triggering can be calculated. So this value of the gate current, which is dependent upon the alpha factor, which is the triggering angle, should be greater than the minimum limit which is required for the reliable triggering. So if you do the firing angle analysis, then for the triggering condition, the thyristor will be turned on when the gate voltage will exceed the trigger voltage. So here we have the Vg as a function of alpha, which is equal to Vgp sin alpha, should be equal to the trigger value. And here this value of the gate voltage, which is the maximum voltage, can be obtained from the resistors as well as the maximum value of the voltage. So this is the peak gate voltage. Firing angle expression we can get as alpha is sine inverse of the expression which we get Vgt R1 plus R2 divided by Vm R2. Control range characteristic where alpha is proportional to the resistor R1 for having the constant R2, and the practical range limitation alpha lying between 0 to 90 degree. So to have the firing angle maximum, it is limited when alpha is equal to 90 degree. Some of the advantages and limitations of this resistance triggering method is that it is simple and inexpensive, it is reliable, and easy firing angle control is possible, low power consumption, and few component is required, which is the advantages. Whereas the limitation is, it is a limited firing angle range from 0 to 90 degree only. Temperature dependent operation is there, no electrical isolation is provided, sensitive to supply voltage variation, gate current flows throughout the conduction process, and the regulation is very poor with load variation. So we use this resistance triggering in the trike applications. We will study the trike in the next lecture. So the circuit can be adapted for trike. So trike stands for triode for AC, by removing the diode enabling the bidirectional triggering. So whenever we require the bidirectional triggering, this one of the resistance triggering method can be used in trike. So this is the circuit that we were talking about, the resistance triggering circuit and its corresponding voltage waveform. So here we can see that there are resistors R1 and R2 and a diode is connected. So R minimum is the summation of R1 plus R2 which is connected. The supply voltage is AC in nature and we will be seeing the voltage waveform. So the voltage which is given as AC will be having the load parameter VL as controlling with the help of alpha. So alpha is the triggering angle and we will be getting the anode to cathode voltage as this. So if you see the output voltage waveform for different firing angle, then this is the input voltage, gate voltage and the output voltage. So this alpha, which is the triggering angle, we will be getting the VGT, which is the gate voltage, and the load voltage will be obtained. Output voltage would be the obtained. So the next triggering method that we are going to see is for the RC triggering circuit. So what are the circuit description? The key components are basically the capacitor, the resistor and diodes D1 and D2. So here we can see more elements are required as compared to the resistance triggering. The principle involves that the capacitor will be charging through the variable resistance and it will control the firing angle. One of the major advantage is that it is extended firing angle range from 0 to 180 degrees. So alpha, which was earlier from 0 to 90 for the R triggering, has now come to 0 to 180 degree for RC triggering circuit. Critical design constraint. So for a proper operation, the RC value, which is the time constant, should be greater than 1.3 times the time period of AC supply by 2, and it is equal to approximately 4 by omega, where omega is 2 pi f, f being the supply frequency. So RC time constant, where the time constant tau is given by the product of the RC value, this determines the charging rate and thus control the firing angle. RC circuit operation in the negative half cycle, if we see, then the charging phase analysis we have to do, which is in the negative half cycle, the capacitor will be charging through the diode D2, and at omega t at minus 90 degree, the capacitor voltage will be the negative of the peak value of the supply voltage. And at omega t minus 90 to omega 2 t 0 degree, capacitor voltage will decrease. The diode D1 function will be to prevent the reverse breakdown of the gate cathode junction. Initial condition at the start of this causative half cycle where omega t equal to 0 degree, the capacitor at the 0th condition will be equal to minus Vm plus delta V. Delta V is needed to account for partial discharge during the transition process. So the RC circuit operation in the positive half cycle, which is the triggering phase analysis, if we do, then the supply voltage become positive here and hence given by the sinusoidal equation Vs equal to Vm sin omega t. Capacitor will be charging through the variable resistor R. The gate voltage, which is given by Vs minus Vc, considering the diode D1. Triggering condition now is the gate voltage is equal to VGT, which is the minimum voltage required, plus the diode voltage Vd, including the diode drop. Capacitor voltage equation during the positive half cycle. So this is the capacitor voltage as a function of time t is equal to the supply voltage Vm sin omega t minus this is the voltage which is appearing in the total capacitor Vm sin omega t plus the initial condition Vc 0 plus e to the power minus t by Rc, Rc being the time constant. Firing angle control mechanism. So if you have the small value of the resistor, then the fast capacitor charging is possible with a small firing angle. If the resistor is large, then slow capacitor charging will be taking place with large firing angle. So the continuous control is possible by varying the resistor. So you can vary the resistor from small or large value, then the continuous control can be possible. RC circuit design parameter you can see to have ensured that adequate gate current is flowing for triggering. So the maximum resistance calculation R should be less than this value, which is given by the supply voltage, the forward voltage drop Vd, and the minimum gate trigger current IGT. So the capacitor selection criteria is required because it should maintain charge during the switching transition. The typical value of this capacitor is 0.1 microfarad to 10 microfarad. The voltage rating should exceed the peak supply voltage and use the non-polarized capacitor for the AC applications. Next, we will see the RC full wave triggering circuit. So this is the enhanced circuit configuration in the form of bridge rectifier, where you will be having the 4 diodes D1 to D4, and this will provide the full wave rectification. The clamping action is provided by the capacitor that maintain the charge reference. The continuous control is there because you have the full wave operation which enable smoother control. This is suitable for application requiring triggering in both half cycle. So when both half of AC cycle is required, we can prefer for RC full wave triggering. This is the full wave operation where you require the RC, which is the time constant, should be greater than 50 into T by 2, which is approximately equal to 157 by omega. If you remember, in the RC half wave triggering, we found this to be 4 by omega. Resistance constraint is that the resistance value has to be less than 4 V minus VGT by the gate current minimum requirement. RC circuit, if we do the comprehensive evaluation, then the advantage is we have the extended range from 0 to nearly 180 degree. This is smooth control because we have the continuous variation. There is good linearity near linear resistor versus alpha. It is simple in implementation, better control than simple resistive network, and low cost solution as well. The limitation, again, it is dependent on the temperature sensitivity, component tolerance effect, limited current capability, there is no electrical isolation, capacitor aging effect, supply voltage dependency. So some of these limitations. Typical applications where we use is in the light dimmer, motor speed controllers, heater controls, battery chargers, and welding equipment. So we discussed these few type of triggerings, and here we will see the RC triggering circuit design. So you can see here the diodes D1 and D2, which is in the half triggering, and there are 4 diodes D1 to D4 in the full wave triggering circuit. So this is the thyristor which is having the gate, and the gate is being controlled with the help of the RC network. So we will be getting the half wave or full wave triggering circuit depending upon how many diodes we are basically using. The voltage and the current waveform for RC triggering circuit, if you see, so this is the input voltage, and we get the rectified output voltage, and the output voltage at the load is given, which is controlled with respect to the alpha conduction. So conduction will be alpha to pi, then pi by pi plus alpha to 2 pi, and so on. So the RC triggering circuit, you can see here the control will be from 0 to 180 degree. Now, one special type of triggering we will discuss, which is the UJT triggering, uni-junction transistor. And the basic device structure, it is a 3-terminal semiconductor device. The terminals involved are the emitter, and there are two bases, B1 and B2. These are formed from lightly doped N-type silicon bar. This is the simple single PN junction formed by aluminum alloy, and two base contacts are there at opposite end. So the intrinsic standoff ratio eta is given by RB1 by RB1 plus RB2. Typical this value of eta lies between 0.5 to 0.8, and the inter-base resistance RBV is the summation of these two base resistor lying between 4 kilo ohm to 10 kilo ohms. So you can see the basic structure of the UJT, which is basically having two base contact at each end of one side of the slot. And there is an aluminum rod which is inserted on the opposite side near B2. So you can see here the base B2 and B1. This is the emitter E, and you have the PN type. So it may look like the aluminum rod is there, which is inserted on the opposite side near the B2. So the aluminum rod will be near to B2, and the B2 will be positive with respect to B1 by applying the base voltage VBB. If you see the equivalent circuit of the UJT, so the diode will represent the PN junction. So here you have the diode which is representing the PN junction of the UJT. So this is the symbol of UJT having emitter and the two bases B1 and B2. The resistors RB1 and RB2 are basically RB1 having variable resistance which will decrease with increasing the emitter current. RB2 is a fixed resistor. So here you can see RB2 is a fixed resistor and RB1 is basically variable. So RB1 range between 50 kilo ohms to 50, and the emitter current will vary from 0 ampere to 50 milliampere. And if you do the electrical characteristic of this UJT, the interbase resistance, which is the summation of the two base resistor, can have from 4 kilo ohm to 10 kilo ohm values. And the voltage, if we compute in the resistor involving B1, when the emitter current is 0, can be given by the voltage division rule involving the base voltage and the resistors RB1 by summation of the two resistors. So this ratio can be given as eta, which is the intrinsic standoff ratio, RB1 by RB1 plus RB2. The emitter threshold potential, which is the peak point voltage for the UJT to turn on, is given by eta times the base voltage plus certain amount of diode forward voltage drop, which is 0.7 volt for the silicon. So we require this much voltage for the UJT to turn on. If you see the VI characteristic of the UJT, which is given by this diagram, voltage current characteristic, which is showing the negative resistance region. So here if we discuss, then the emitter voltage when exceeds this voltage which is required for turn on, the emitter will fire and it will inject the holes in the N-type slab. There will be increase in the hole current which will enhance the conductivity, and the emitter voltage will drop as the emitter current increases, entering in the negative resistance region. So UJT basically functions in the negative resistance region and passes through the valley point, which is given by IV valley, become saturated. So the curve, the emitter voltage and the emitter current, these are basically the valley points for the current and the voltage. So here you can see the IV value, and this is what you have the peak amount of the current, and this will be the negative resistance peak point. So here you have the saturation region. What is relaxation oscillator in the context of UJT? So relaxation oscillator basically uses the UJT to generate sawtooth waveform. So when we require sawtooth waveform, then we require UJT, and that is basically known as the relaxation oscillator. This will operate by storing the energy in the capacitor and dissipating it repeatedly. So the capacitor will charge toward the positive supply until the threshold voltage, which is given by Vp. We have already done the expression for Vp, and upon reaching the threshold limit, capacitor will discharge rapidly. So the key circuit components now, we have the UJT, which will provide the switching action. There is a capacitor, which is energy storage element, and this is charged through the emitter resistor. The resistor R1 will discharge path for the capacitor, and the supply voltage is basically the DC power source. If you see the working principle of the operating sequence, the capacitor voltage will increase exponentially until the peak point voltage is reached. And when this voltage is reached, UJT will conduct and the capacitor will discharge rapidly through the emitter base B1 and the resistor R1. After discharge to the valley point voltage, capacitor will begin charge again. This process will repeat to generate the continuous conduction. So this is the operating sequence of the relaxation oscillator. The charging time constant is given by tau 1, which is the emitter resistor multiplied with the capacitor value, and the discharge time constant tau 2 will have the two resistors R1 and RB1 summation multiplied with the capacitor. Since the emitter resistor is quite greater than the summation of RB1 plus R1, we will always have the tau 1 value to be quite high as compared to tau 2. Now this is your relaxation oscillator. If you see it, this is your UJT, and in the UJT, if you see, the resistors R2 and R1 are connected to the base B1 and B2, and this is your emitter resistor RE, and there is a capacitor which is connected. So this is the UJT relaxation oscillator configuration with different voltages and different the values of the resistors are shown. These are typical values of the resistors shown. So you will be getting the sawtooth waveform, which will be generated across the capacitor Vc, and these signal whatever we have given, we are basically getting the sawtooth signal. So this is your emitter voltage with respect to time t and the resistor R1 voltage. So you can see the time constant tau, which is dependent upon the resistor value of R1 and RB1 and the capacitor value. So this will be controlling and provide a sawtooth voltage. If we do the timing analysis of this UJT relaxation oscillator, charging time constant is the product of emitter resistor into C, and at time t1, the capacitor voltage is equal to the Vp value. UJT will be turning on and the capacitor will discharge through the resistor R1. Discharge occurs during duration t2 until the capacitor voltage is equal to the valley voltage, which we can see it here in this ratio. This is your t2 time and this is your t1. So discharge process is basically taking in this zone. Charging time and discharge time, both we can do the mathematical analysis which depend upon the resistor capacitor and the different voltages, the valley voltage and the peak voltage, the supply voltage. So we can have the mathematical analysis. When we talk about the oscillation frequency, the total cycle time t is given by the summation of these two time period t1 plus t2. And since the time t1 is very greater than t2, the oscillation frequency can be approximated by this expression, where here eta is basically the intrinsic standoff ratio of the UJT. The other parameters are the emitter, resistor and the capacitor. So the frequency will depend upon the charge time constant and the UJT characteristic. Some of the key features is that it will be generating the sawtooth waveform due to cycling of charging and the discharging process. The UJT will provide negative resistance during the discharge process. It is a simple circuit design with few components, and we can use this application in timing circuit, pulse generation and waveform generation. So this is the circuit figuring of UJT for a Thyristor control, where you have the UJT and the resistors are connected R2, R1, there is a variable resistor and the capacitor, and a DC voltage is given here. So external resistance R1 and R2 are smaller than the internal resistor of the bases. Charging resistance R ensure that the load line intersect in the negative resistance region. So you are basically using one of the charging resistor R because you have to intersect the load line to the negative resistance region. Now, capacitor charging phase, when the DC voltage V is applied, then the capacitor will charge through the resistor and the emitter will remain open circuit during this charging process, and the capacitor will have the voltage Vc given by V into 1 minus e to the power minus t by tau 1, where tau 1 is the time constant given by Rc. This is the charging time constant, tau 1. And the UJT turn on discharge process, if you see, then when the capacitor voltage will reach the Vp value given by eta V plus Vd, the emitter base 1 junction will break down. UJT will turn on and the capacitor will discharge through the resistor R1 with the time constant T2 being R1 into C. Now, since the time constant T2 is very less than T1, there is a rapid discharge occurring and the emitter voltage will drop to the valley voltage, current will fall below the IV and the UJT turned off. So, this is the discharge process of the UJT turning off, and here you can see the voltage and the current form of UJT triggering circuit. You have the capacitor voltage which is going in the charging and the discharging process with the time constant tau 1 and tau 2. So, there is a charging and discharging continuous process, and there is a voltage of the base B1, you can see it here. Now, if we see the design equation to compute the peak voltage which is given by eta V plus Vd, this depends upon the valley voltage, the supply voltage at the time constant, and t being the oscillation period, we can compute the intrinsic ratio eta, the time period being 1 by frequency given by Rc ln of 1 by 1 minus eta. The firing angle alpha 1 is given by omega t, where t you can easily substitute as Rc into ln of 1 by 1 minus eta, omega being the angular frequency of the supply. UJT triggering circuit, if we do the design consideration, then R1 must be small to keep the leakage current drop below the peak voltage, and the condition for the SCR to trigger voltage is given by this condition, where the VGT should be greater than this value determined by the base registers and the different registers. RBB is a summation of the two base registers. So, the design guidelines is the R2 is equal to 10 to the power 4 by eta into V, and the triggering pulse width approximately equal to R1 into C. The resistance limit, if we see, then the maximum resistance and the minimum resistance are basically calculated with the help of the valley voltage, the supply voltage, and what is the peak current, the valley current, and the intrinsic standoff ratio. Now, let us see the advantage, limitations, and the applications of UJT triggering circuit. So, advantage, if we talk about, then we get a sharp triggering pulses because you have the high di by dt, which is reliable triggering. There is electrical isolation through the pulse transformer, and temperature stability is also there because better RC circuit we are using. Precise timing is possible because accurate firing angle control can be possible. Low power consumption because it is efficient operation, and you have the wide firing angle range 0 to 180 degree. On the other hand, the limitations are it is higher cost compared to the RC network. It is more complex circuit design. The UJT parameter variations are there with respect to temperature. It will require additional component for isolation. The application, industrial motor drive, we can use high power converters, welding equipment, induction heating, and precision timing applications. So, this is the applications of UJT. Now, we have already covered R triggering, RC triggering, UJT triggering. Now, let us go with some other techniques like transformer coupled triggering. So, if you see the circuit features, here you have the electrical isolation, which was not possible in any of the earlier triggering methods. So, you have the complete isolation here between the control and the power circuit, and you require a pulse transformer. This will provide the coupling and the isolation, and you will have the sharp pulses because of high di by dt for reliable triggering. The design consideration, you require the transformer turns ratio, which is given by number of turns in the secondary by number of turns in the primary, N2 by N1, and the primary current and the secondary voltage can be computed very easily with the fundamental equations I1 and V2. The core material you can use ferrite for high frequency operation. Applications, when we talk about, then it is used in high voltage thyristor applications, multi thyristor system requiring isolation, industrial control system. So, this is again another type of triggering method which is optically isolated triggering. So, as the name states that optical, so you have the light source. So, Circuit components involve the LED, which is the light source for optical coupling. You can have photodiode or phototransistor, which is the light detector, optical coupler, which provide the complete electrical isolation, and the drive circuit, which control the LED current. Advantage, it will have again the isolation, complete isolation, because no electrical connection is there. High voltage capability is there, can handle the voltage in the kilovolt range. Fast switching is possible, nanosecond response time. Immunity to noise, because it is excellent to EMI or RFI injection, and it has the longer life because there is no mechanical system to be wear and tear. Design parameters, the current transfer ratio is given by IC by IF. Isolation voltage is typically in the range of 2.5 kilovolt to 7.5 kilovolt, and the response time is in few microseconds. Now, this is the complete comparison of the different triggerings, R triggering, RC triggering, and UGT triggering. So, the firing angle range, if you see, R triggering is the poorest, 0 to 90, other you have 0 to 180 degree. R triggering is simple in terms of circuit complexity, but RC triggering is having moderate complexity, UGT is complex. In terms of component, you require R triggering low component, but high component in UGT and moderate in RC triggering. Isolation only possible with respect to transformer in UGT, otherwise it is not possible. If you talk about the temperature stability, then it is good in UGT, but poor in R triggering and fair in RC triggering. Cost is high in UGT, other you have low. Pulse quality excellent for UGT, but poor in R or RC. Linearity, if you talk about, again excellent in UGT. Load regulation is good in UGT, application wise high end control. So again, if you see all combined, the UGT will be preferred over the R or RC triggering. These are the main classification of the triggering method. Now, if we see the circuit selection guidelines, the selection criteria, talking about the firing angle range, then choose RC or UGT when you require full range control. Talk about the isolation requirement, UGT you can use with pulse transformer for isolation. If you talk about the cost, then R circuit is the cost sensitive application. If you talk about the temperature stability, then UGT can be used for harsh environment. Pulse quality, UGT can be used for applications involving sharp pulses, and load regulation, again UGT is better. So combining all these factors, if you can see again, majority of the cases the UGT will have upper and advantage. So specific application, R triggering you can use in simple heater control, basic lighting application. RC triggering you can use in motor drives, power supplies, and light dimmers. UGT triggering generally used in industrial motor drive, high power converters, and welding. These two special category, transformer coupled and opto isolated, are used for, again, where you required isolation and you have the system involving the lights, which is especially in the medical equipment or safety consideration. We require the gate to be protected. So gate protection is very important, and the essential protection technique involved the series resistance, linear diode, reverse diode, RC snabber circuit. So this we have discussed in detail. The gate cathode resistors. So these all protection methods are very important when we talk about the gate protection. So there are certain design guidelines that we need to follow, like the gate current should be around 2 to 5 times the minimum threshold limit for reliable triggering. The gate pulse width should ensure anode current reaches the latching current. Consider temperature effect on the gate characteristic. Provide adequate heat sinking for gate drive circuit, and use bypass capacitor for noise immunity. So gate protection is important and proper guidelines need to be followed. Again, we need to do the thermal consideration, EMI and RFI consideration, and some of the safety consideration. This is again important when we are properly designing the network, and these all considerations play important role, and we need to do very importantly in terms of the different parameters using the cables or the ground loops, the layout, and some of the safety consideration in terms of the isolation, creepage distance consideration, and fault protection. This will be used in the design phases. Now, modern gate drive technologies are there, which is basically IC-based gate drivers. Some of the advanced features are also coming, and the modern applications generally involve the variable frequency drives, the UPS systems, electric vehicle charging systems, and renewable energy inverters. So nowadays, apart from the ordinary RC or this UGT triggering methods, we have some IC based gate driver methods where we can see this advantages because they are providing most isolation, control, built-in protection, and you can have over voltage, over current protection as well, where you can have these IC based gate trigger networks. Now, some of the key learnings that we have studied, let us revise it, that we have the thyristor operation, which is very important, triggering methods which are important, gate characteristic is very important, circuit analysis is required, design methodology is also required. So, practical skill needs to be developed in terms of selecting the appropriate triggering circuit, design calculation for component values, understanding the protection requirement, and troubleshooting some of the common problems. These are the most important formulas that can be used for the design formulas for the triggering in terms of the firing angle, the RC timing constant, the UGT frequency, gate power, peak point voltage, and the design consideration involving the gate current and gate voltage and the gate power should be properly limited. Otherwise, the system may not function well. So, these complete our discussion on the different triggering techniques for the thyristors. In the next lecture, we will see some of the thyristor families like the diode, diac, and the triac. Thank you for now. See you in the next lecture.